Hello everyone. So let's talk about the trial division property of prime number. So the trial division property of prime number says that if n is a positive integer number, then n has a prime divisor less than or equal to square root of n. So it's saying that m is a positive integer number for any number, any positive integer number. Let's say n equals to 100. Okay, so this number will have a prime divisor which has to be less than or equal to square root of n. So n will be divided, n will have a prime divisor, all right, which has to be less than or equal to 10. All right, as we know that n will have a prime divisor, like n is divided by 2 and 5. Okay, n has a 2 and 5 prime divisor, so they both are actually less than or equal to 10. All right, so now actually we are going to see how we can prove this theorem. All right, so this trial division, this property is actually a very important property. We can use this fact, we can use this property of prime number to determine whether given a number is a prime number or not. All right, all right, so let's see whether we can prove this fact. All right, so we are saying that if n is a number, n is a positive integer number, n will have a prime divisor, and that prime divisor will be less than or equal to square root of n. All right, so let's see, we are saying that n is not a prime number. All right, so n is not a prime number, so obviously n will have we can represent n as a factor of, let's see, a and b. All right, so in this case we can assume that so we can say that n can be represented as a factor of a, as a multiplication of a and b. All right, and where a will greater than 1, and let's see, a is less than or equal to b. All right, so a is the smaller factor and b is the larger factor, and both of the number a and b has to be less than n. Okay, so a and b can be same. For example, like 4, I can represent it as like 2 and 2. All right, 2 times 2, like that. So a and b can be same, but let's see, if a is less than b, in that case a will be the smaller and b is the larger factor, and if they are same, then they are same, but both are, whereas both has to be less than n, right? All right, so okay, so let's see, a is greater than square root of n. All right, and b is greater than square root of n. Okay, we are just assuming that. Let's assume a is greater than square root of n, b is greater than square root of n. So what does that tell us? A, b has to be greater than n. All right, but this is a contradictory. All right, ab cannot be greater than n, ab is same as n, so that's tell us that a has to be less than or equal to square root of n, or b has to be less than or equal to square root of n. All right, so if n is a composite number and n has any two prime numbers, prime factor, all right, in that case any one of them has to be less than or equal to n. All right, so let's see, a is a prime factor. Okay, b is just another factor. Let's see, a is a prime factor. All right, and b is just a normal number. Let's just say assume that. Okay, then I'm saying that so then it proves our theorem. If a is a prime factor and b is normal number, then it proves our theorem that one prime factor has to be less than or equal to square root of n. All right, now let's see, a and b, none of them are prime number, but based on our previous theorem, it says that any number, any normal number, we can actually represent them as a factor of prime number. Okay, So if a is not a prime number, in that case we can represent them as a factor of some prime numbers. So that means there is a prime number who divides a. All right, now a divides n. Okay, and that will tell us that p divides n. Okay, so that's the transitivity rule of the division. So if p divides a divides n, and then the prime number will divide the natural number n. And p divides a means actually p is less than a. Okay, less than or equal to, p is less than or equal to a. All right, so it's again proof that there is a prime divisor who is less than or equal to square root of n. All right, so in our chapter, that's 4.3.4 lemma. Okay, so you can go and read over one more time, then you will have actually the good idea how to prove that. So let me just go over again. So let's assume that n is a composite number, so we can divide n as a factor of we can represent n as a multiplication of a and b. Okay, if both a and b is greater than square root of n, that will prove that ab is greater than n. So which is a contradiction, so that means one of the number has to be less than or equal to square root of n. Now any one of the number, based on the prime number rule, each number can be represented as a multiplication of some prime number. Okay, so that means let's just assume any number a or b. So this number can has at least one prime divisor. All right, so let's just, the prime divisor is p. P divides a and a divides n, so that means p divides n. So as p divides a, so p has to be less than or equal to a. That means p has to be less than or equal to square root of n. Okay, so that proves that any number n has a any number n has a prime divisor which is less than or equal to square root of n. So this fact, we can use this fact, the trial division, to determine whether a number is prime or not. Okay, so how we can prove that? Let's see, you have any number, pick any number, let's say 539. All right, so given a number n equals to 539, we want to determine that whether this number is prime or not. Okay, so one of the naive approach could be like just try to find out all the numbers, think about all the integer numbers less than n, and try to see whether that number divides 539 or not. So if we find that this number doesn't have any divisor which is other than 1 and the 539 itself, then we can say that it's a prime number. Okay, but as you can see that this number 539, all right, now I cannot think of considering all the numbers less than 539, and I cannot think about that whether these numbers divides 539 or not. So here we can use the trial division approach to determine whether the number is prime or not. So the trial division says that for any number n, okay, so it will have a prime divisor which will be less than or equal to square root of n. All right, so square root of 539 equals to, it's like actually 23.216. all right, so now to determine whether this number n is a prime number or not, we are going to consider all prime numbers less than or equal to 23.216, or less than or equal to 23. Okay, so all prime numbers less than or equal to 23. So that's the list of the number we are going to check, and we are going to see that whether it has a prime divisor which is less than or equal to 23. So let's just make a list of all the prime numbers. So the first prime number is 2, then we have 3, then we have 5, 7, okay, so 11, uh, 13, we have 17 prime number. All right, then I guess we have prime number 23. Okay, so these are the number we are going to find out whether this any of the prime number is a divisor of the number given number 539. Okay, so there are 1 2 3 4 5 6 7 8, these 8 number we have to check. So we are going to find out whether 2 divides 539 or not, 3 divides 539 or not, 5 divides 539 or not, like that. Okay, and we are going to keep going on. Now here there are some rules. Actually, we know that if the number is a odd number, 2 doesn't divide. Okay, now 539, whether it is divided by 3 or not, there is a simple rule. So just add all the digit. Okay, like 5 plus 5 plus 3 is 8, 8 plus 9 is 17, 17 is not divided by 3, so that means this number is not divided by 3. Okay, so 5 doesn't divide 539. All right, so how about 7? So then so 7 divided 539. So here we can see that actually 7 of it's 49, so 49 77. Okay, so 7 actually 7 divides 539. All right, so and the result is 77. Okay, the quotient, the result is 77. So here we can see that there is a prime divisor. Okay, so 539 has one divisor. All right, 539 has one divisor other than 1 and 539 itself, so that's not a prime number. All right, so as we said that this trial division is actually very important to find out whether a number is prime or not. Okay, and using this formula we can find out also all the list of prime numbers not exceeding a certain integer number. Okay, so the sieve of Eratosthenes is a method of finding all the prime numbers not exceeding a certain integer number. All right, and here also we are going to use the fact of the trial division. Okay, so what actually we are going to do, first we are going to delete all the numbers that is divided by 2. Okay, so all the numbers deleting multiples of 2 except 2 is a prime number. Then we are going to delete all the numbers multiples of 3 except 3 because 3 is a prime number, and then all the multiples of 5. Okay, and we are going to continue up to the largest prime such that a is less than or equal to square root of n. Okay, so let's see one example. Okay, so we are going to find out all the prime numbers less than we are going to find out all the prime numbers less than or equal to 20. Okay, we are going to find out all the prime numbers not exceeding a certain integer less than or equal to 20. So I have all the prime numbers 1 2 3 4 5 6 7 8 9 10. Okay, so let's make it 30. All right, so let's see a equals to 30, and we're going to do okay. So we're going to find out all the prime numbers not exceeding a certain integer 30. How we can do that? We are not going to consider 1, okay, because 1 is not either a prime or a composite. All right, we are going to start from 2. So first we are going to delete all the numbers multiples of 2, means we are going to delete all the even numbers. Okay, so except 2 is prime number, so we are not going to delete 2, but we are going to delete all the numbers that is divided by 2. Okay, so 4 6 8 10 means all the even number. Okay, so we are considering a equals to 30, means we are going to find out all the prime number not exceeding 30. So before that we have to consider the number a square root of 30, which is um, which is actually 5 point something. Okay, which is 5 point something. So we are going to actually we are going to do that. We are going to continue our this approach for that means we are going to actually find out all the multiples of 2, 3 and 5. Okay, we are going to find out all the multiples of 2, 3 and 5. So let's do that. So now we are going to delete all the numbers multiples of 3 except 3. Okay, as 3 is the prime number, so let's delete all the multiples of 3. So we're going to delete 6, 9, 12, 15, 18, then 21, okay, 24, 24, 27, 30. Okay, then I have to consider 5. So I'm not going to delete 5 because 5 is a prime number. So I'm only going to delete all the multiples of 5 except 5. Okay, so 5 will be there, but delete all the multiples of 5. So 10, 15, 20, 25 and 30. Okay, all right, now we don't have to consider any other prime numbers greater than 5 because that's actually our trial division. Okay, that's our trial division is saying that we have to consider only all the numbers less than or equal to square root of 30. Okay, so now just find out which number has not been crossed. So we can see 2, 3, 5, 7. Okay, we have here 11, 13, 17, 19, 23, 29. Okay, so these are the list of our prime numbers which are less than or equal to 30. Okay, all the prime numbers from 1 to 30, these are the list of prime numbers. All right, and you can actually consider any of the numbers. Like if you want to find out the numbers, prime numbers determine all the prime numbers up to 100. Okay, you can consider the same algorithm to find out all of them. Okay.